Next, we have Andy Driesman. Very pleased to have Andy here today. From the beginning of this study, we have looked at Parker as a model, not just for instruments in some cases, but as a program. What does it take for a heliophysics large strategic mission to come together? And he's going to share with us some lessons learned from the execution of that mission. Andy was the program manager for many years on Parker Solar Probe until after launch. And he's going to share with us lessons learned here. And Andy, the virtual floor is yours. Thanks very much for being here.
Okay, thanks, Michael. So as it indicates on the title slide, I've given this presentation a couple of times, once to the Space Studies Board. I want to say that was in 2020, and then I did a slightly different version for the planetary decadal, I think it was the panel on Mars, all sort of asking the same question, what could we learn from, a flagship type mission that by all by all metrics, technical, cost, and schedule performed very well. And all I can say is I hope that in 20 years from now, I'm listening to the very same version of this conversation, only ISP is featured because you have launched as planned in 31, and 2040 is probably the transition date for many on the project. So why don't we go ahead and go to the next slide. Okay, so I'm going to give a little bit on the historical perspective of Parker Solar Probe. It is amazing as I was reviewing these slides, the parallels with ISP in terms of some of the history. Give you a brief look at the mission, the system overview, hit some of the science discoveries. In particular, I'm going to highlight what I would call non-mainstream science. These missions are planned and deeply planned with science expectations and requirements, but it's always interesting how the collateral science is as exciting. And so in many ways, the collateral science is much more in tune to the public because of the nature of the heliophysics mission, though the heliophysics discoveries are frankly awe-inspiring. Lessons learned. I'm going to focus lessons, what I would call enabling lessons learned. So these are the positive things, as well as some lessons we learned the hard way, and then hopefully leave some time for discussion. Next slide, please. You guys, there we go. oh, come on. So Parker Solar Probe's history. So the mission started in 1958. I have not done the detailed day-by-day analysis as to whether Parker predates NASA, but it's very close. And this was a mission that was defined in some of the Simpson reports. Parker, the namesake for the mission, wrote a seminal paper in '58 predicting the existence of the solar wind. And the Simpson committee posited a mission that was actually called Solar Probe that was to go into that needed to go into the inner heliosphere to understand two basic things: why does what is accelerating the solar wind to escape velocities, and what causes coronal heating. So the thing being that the corona is significantly hotter than the surface of the sun. To do this, one needed to go to the place where these things are generated, which is pretty close to the sun. And then through '58 to 2007, I would call that a big technology gap. Just the materials and the ways of thinking about these missions did not exist. In the late 2000, 2007, 2008, there was a number of reports looking at reimagining Parker. So rather than going out to Jupiter, doing a Jupiter flyby, sound familiar, and then diving deep into the sun for one or two very short passes, a team at APL envisioned a mission where we could go not quite as deep, say 10 solar radii, but spend a lot more time in the region of interest. So here you've got here the milestones. Phase A started in 2009. We launched at 3:31 a.m. on August 12, 2018. And sometime in 2017, Solar Probe Plus became Parker Solar Probe. Next slide, please.
Sorry, Andy, there seems to be a lag from when I advance to when it updates.
That's okay. It's a pretty dense file. Regardless, this is a picture of the spacecraft or a cartoon image. You can see on the right and center. And these are the artist rendering of what this would look like in orbit. The thing that protects Parker and was probably one of the biggest technology development efforts is a thermal protection system. It's 4.5 inches of carbon foam between carbon face sheets with an optically white coating on top that rejects a good portion of the incident heat. At closest approach is about 3 megawatts of energy being deposited on that heat shield. Everything behind that heat shield is roughly at what would say, let's call it a room temperature without air conditioning in Florida. So very balmy, but certainly well within the operating constraints of most of the electronic systems that we fly on spacecraft. The power on Solar Probe is generated photoelectrically by solar rays. So these solar rays are generating power even at the closest approach to the sun. And to keep them cool, there's an active cooling loop with deionized water that's pumped through the solar rays and out to a series of radiators you can see just tucked behind the thermal protection system. The data return is through a high gain antenna. And then the instruments, we've got a large array of instrument suites measuring everything from the electromagnetic environment around the spacecraft to low and high energy particles to plasma around the spacecraft. And then finally, there is a white light imager that has 2 cameras that are sense enough to actually image the corona. Next, oh, and I should point out at the right, one of my favorite pictures is the spacecraft sitting in the one half of the fairing on the Delta IV Heavy just before shipping to the launch site. You notice that there's a third stage tucked under it, which is were required for the mission, and it was not part of the Delta IV Heavy. It was a separately procured stage. So solar distance and implications, probably preaching to the choir in terms of the people in the room, but you could see in blue in the center there, in the center there, you can see the Solar Probe orbits. It does 24 orbits before it completes its mission success. It intersects Venus 7 times during that flyout. And every time it intersects Venus, it exchanges energy with Venus and drops the perihelion slightly closer to the sun. But even after day 1, we were well within the closest approach of any other spacecraft. You can see Helios B sort of drawn there in blue. And within 3 months of having launched, we were at a close approach to the sun. And then we're currently heading towards our V5, our 5th Venus flyby, which will drop the perihelion a little closer. We're actually now accumulating hours for mission success, so it's very exciting. So I'll point out a couple of implications that come with say, we're going to do Solar Probe, and these are things that just are. The first is there's an unknown, unexplored region of the solar system we're going to. That had the interesting effect, and Jim could talk at length about this, but it forced a very tight coupling between the engineering teams and the science teams. There were no handbooks, there's no radiation tables you could look up, there's no experiential data on being that close to the sun. So much of what drove the engineering was derived from raw science or raw science predictions and models. So there was right off the bat a very tight coupling between the engineering and the science. The orbit is highly dynamic. You're moving very quickly. Unlike many of our missions, you pick on Mars, I'll pick on ISP even a bit, there's no crews per se right off the bat, we launched within 6 weeks. We're at Venus. Another 6 weeks, we were closer to the sun than any other spacecraft had been before. And then, boom, you're out again. And that just gets tighter and tighter as the orbit gets smaller and smaller. There's a hypervelocity dust environment. Meteors and comets leaving dust, as well as the zodiacal dust. And it's something that we predicted and did a lot of experimentation with prior to launch. And it's something that the spacecraft is very much experiencing. So there's two aspects. That there's the engineering experience. Oh my God, we're getting pelted by hypervelocity dust. And then there's a science experience going, oh my God, this is great. We're getting hit by hypervelocity dust. So there's two very different perspectives on it. The mission is unforgiving. For much of the mission, even minor excursions in attitude will cause loss of missions. I'm talking 1 to 2 degrees. The reality is most spacecraft, you can tumble and they'll recover. Parker doesn't have that luxury. So the emphasis on fault management was keen. And then finally, poor or no communications. For much of these orbits, we're in conjunction with the sun. Either the Earth, sun, and spacecraft are aligned. And that drove a lot of the concept of operations as well as the fault management, is that the spacecraft had to be self-sufficient. So the autonomous protection systems in there had to be well understood, predictable, robust, and well tested. Next slide, please. So quickly, some science discoveries. This was one of the earliest discoveries. This is the discovery that the actual magnetic field of the sun does not follow the predicts we predicted. The change of polarity and the high rate of change of polarity is something that caught the scientists unexpected, and it's being even investigated to this day as one of the primary means of moving energy around the solar system. In the lower right corner, there's the model is in red, and then the actuals are in black, the actual measurements, and you can see the crossing of the 0 line, which was somewhat unpredicted. Next slide, please. You guys still there?
Yes, we're still here. The slide is taking quite a while to change.
Okay.
I'm going a dust disk around the sun. We're on that slide. Hopefully it updates.
Okay. The other was, since 1929, there was predicted that there would be a dust-free zone around the sun. So this is where the sun either ablates the dust environment close to itself, or the solar wind drives the dust out of the environment. But it was impossible to see. And this data from 2020 gives the first indications that such an environment does exist. So once again, something predicted, oh, it's almost 100 years ago, is now being verified by Parker. Next slide, please.
I think the entire Zoom system is just tired of us after 4 days of this so far.
5 days, you've ran out of your bill. This is particularly exciting. So as I mentioned, Parker uses Venus to pump down its orbit. And though not planned, we turned on all our instruments as we flew by Venus in an attempt to provide information to the Venus community. And what you see here is a white light image of Venus. But what's surprising about this image was the fact that we could see to the ground. So in the middle there is a colorful radar, color enhanced radar image. And on the left there is the Parker image. And we did not realize that Whisper, which is the imager, had sensitivity to at these frequencies. So this is striking that we could see to the ground. Next slide, please. So into lessons learned. The first lesson learned I'll offer is that it was one team, one mission. Mission success was the single objective. I have never worked with a closer, tightly bound team. And when I see team, I'm not only talking about the team at APL as well as the principal investigation institutions, but I'm talking all the way up to NASA SMD. I think there was an understanding that Parker, whether to fail, God forbid, technically, but cost and schedule wise, was more impactful of NASA MD than it was the people working on the project. Where, I would certainly take it very personally and be, it would impact me greatly. The reality is I would move on to another project and start working that. The failure of Parker on any of those grounds for an SMD directive would have unwinded the vision and the strategy and the programs that had been planned. So in many ways, as you go up an organizational chart, the impact of the risk goes higher, yet the ability to mitigate the risk is something that occurs very low in the organization. So we have this duality that has to be managed. And the way we managed it is the development of trusted communications. Very early on, there was an emphasis on the importance of cross-institutional leadership, training, and trust. And we worked very hard to establish these relationships. And they frankly are what got us through it in the end, as we built a single team that were able to communicate and trust each other. Next slide, please. Back one. Budget is budget, and budget is the energy that a project runs on. I can't emphasize enough that Parker had almost an ideal budget profile. This credit goes to whatever magic they did at headquarters, but we at no time at the project ever had to slow for funding concerns. We were always sufficiently forward funded. When we asked for reserves, we typically gave a significant warning ahead of time, and reserves were offered. And that allowed us as a management team to focus on schedule performance, not so much on cost performance. Cost follows schedule. And so if you could keep things moving and keep the team well fed, i.e. funded, you have your best shot at mission success. Next slide, please. This goes a little bit without saying, that invest in technologies early, it's the mantra, but what NASA and what APL did is we didn't just fund the technology development, we funded the system around the technology development. I think it's a mistake that we avoided to just invest in technologies without investing in the system. Technologies will develop on their own perfectly well, but if you don't invest in the system, when those technologies are mature, they hit the system and you get a discontinuity. So there has to be a fair amount of investment in system development along with the technology development. And it is particularly important with highly coupled systems, and Parker was a highly coupled system. And I'll point out that the science and the engineering teams work very well together. There were often trades where science performance was traded for technology stability. So holding on to those 19th and 20th level science requirements needs to really be thought of in the face of technological and programmatic risk. Next slide, please. Early milestones are just as important as the later milestones. Everybody, it's human nature, right? You get towards a due date, you suddenly realize that you had scoped out only a portion of the work, and now you're realize that you only have 5% of the time for 20% of the work. I give the team a lot of credit in that it was recognized very early that we were going to struggle to meet the launch date. So this was the first program I've been involved with, which really just took it by the horns, and double shifts were started 2 years prior to launch, understanding we needed to accelerate the milestone closures and getting the work behind us if we had any chance to meet the launch date. I'll point out that the launch of Parker, the 2018 launch date, was probably the best of the class. There was a backup window in 19, which had significantly degraded science. And then after that, the next launch date was in 2023. So the team was incentivized to launch in 2018. And finally, just a note is all this is enabled is that Parker launched on time at a cost well below agency budget. Next slide, please. Complexity and institutional team experience with complexity is a knife that cuts two ways. How you manage complexity is very important. APL, which was the mission implementation center for Parker, had a lot of experience with less complex systems. So as we grew into Parker and discovered the implications of complex systems, we didn't necessarily have the processes and the right people in the right place to deal with the complexity. This created stresses in the organization. It created stresses in the performance. The opposite is true as well. If you have organizations that are used to dealing with complex system and you ask them to step it down to something less complex, you often have the opposite problem where you have this baggage of oversight and process that makes sense in a complex system, but becomes burden and baggage when it's pushed into a non-complex system. So the recognition of this is important. This is not something Parker did particularly well, but it's something that we are taking into the future as we're developing our future missions. Next slide, please. So this is my get off the stage slide. Sorry for rushing here a bit. So there was a vision established 60 years ago for Parker Solar Probe. It was an audacious vision going to a place in the solar system where, it does not take a lot of engineering or science imagination to know how harsh the environment is. Yet we as an industry or community for 60 years have been pushing on this rope. And finally in 2018, after a lot of advocacy within the community, and applause for the ISP team, right, by the way, this became a reality. The spacecraft is fully operational. It's heading into its ninth or 10th perihelion. Jim can correct me, but it's returning science at a rate unexpected. And every orbit is yielding new discoveries and insights. There is data that's embargoed. There are wonderful discoveries being made, and I'm very excited to have been a part of it. But most importantly, and if there's a single message that I'd like to come out of this, and it's a charge to the community, not just ISP, is that we can do daring high technology missions of exploration. We can do them within budget, and we can do that within scheduled commitments. But it's not going to come naturally. We do have to establish the teams to be able to do that. So I'm excited about ISP. I think there are a lot of parallels here, and I think it can be done responsibly and within the community. And we have a community that's suspicious, right? We've had many overruns. And so it's particularly as we go into the decadal, you could bet a lot of money that there are going to be discussions about, oh, ISP costs XYZ, and do we really believe that number? Anyway, I'll get off the stage. I think I have a few minutes here for questions.
Yeah, thank you, Andy, very much. With Ralph McNutt, leading this project, and Jim Kinnison on it, these parallels between Parker and Interstellar certainly have come up over and over again. And we might have even been perhaps applying some of your lessons learned as we were going on, even before you started presenting this, without knowing it. I mean, we do have a couple of minutes. I know that you've got a hard stop at 2 o'clock sharp. And if you want to ask any questions to Andy while he's here, we'd welcome them. We do have one question from Nibbin, who asks, could the heat produced from RTGs be used in maintaining an ideal temperature for the instruments, as is done on the Mars Perseverance? I can take that one. I can say that yes, but usually routing electrical wires with heaters at the end of them is a more mass efficient way to do that. And we certainly have the power to do it. And when we run our instruments, they usually put off enough waste heat to keep themselves alive and warm anyway. That's a balance that comes out of the design. Jim?
No, just going to add with thermal blankets and heaters, we are perfectly able to do that with a minimum mass.
All righty. I love the slide you've got here, Andy, for discussion. Let's see what lies ahead. Yes. Well, thank you all for Andy. Thank you very much for making time to share this with us today. We definitely do see Parker as part of the family of missions that that Interstellar Probe fits in, and it's really great to have you here. Thank you all for joining us. As you all know, we have our poster session starting at 2:30, and that's over in Gathertown. Hope that you can join us there and see the posters that our colleagues have provided for the conference. And Nibbin's got another question about orbital dynamics that I'll take offline. So thank you all, and we'll see you again tomorrow morning. Ended on a great note here with Andy Driesman today, as well as our guests June and Rob from NASA. Thanks again. Catch you at the poster session and tomorrow morning. Have a good day, everybody.